Welcome back. So today we are trying to solve one problem which it's kind of a interesting problem to solve. The main idea of this problem is not to implement just a trie data structure, but to think about the rationale behind what our trie data structures are, and on top of it, what is a bigger implications and practical applications of such data structure is, and at the end, how do we make it as a clean code, basically in kind of a system design round, not for the sake of interviews per se, but also generically how would you try to tend to make it a library, right, for a fellow developer to use, or something of that sort. So yeah, it's a packed content, I would say. Let's start with this implementation and see like how we can build upon it till the very end, right? So for that to start, we have to at least bare minimum try to solve this problem first, and then we can eventually build upon it. So it would be bit of a lengthier video. Yeah, so first let's try to get an optimal solution first, and then iteratively improvise and see like how we can build up to a good library, right? At least a starting point of a library, right? So yeah, without further ado, let's get started with implement trie, a prefix tree, right? So as the problem statement goes, a trie, pronounced as trie, a prefix tree is a tree data structure used to efficiently store, retrieve keys in data set of strings. There are various applications of this data structures. As we all know, it is for a type ahead, autocomplete, and spell checker. Particularly, I think for spell checker, there is something called as a Levenstein distance that we need to calculate. But then that's a bigger picture of what a trie could land up us into. But yeah, first let's solve this problem. So implement the trie class, right? Trie as a class, what is that we need to implement here? Trie initializes the trie object. So they have given a public constructor which initializes whatever the internal data structure that we will tend to use. We will try that trie would discuss it, or would then initialize that. And then insert would do, obviously, what does an insert do? Insert would take up a word and then put it into our data store, right? That is what they have given. Insert the string of word into trie. Boolean search string of word returns true if the word is in trie, that is was inserted before, and false otherwise. As the signature of this method suggests, that it would go ahead, right? It will go ahead and then search in our data store, right, for this particular word. If it is there, then return true, otherwise, as the method says, that it need to return false, right? And starts with, that's where the trie as a data structure comes in handy, right? So return true if there is a previous inserted string word that has a prefix, whatever the prefix that is, right? It's kind of a substring, but then the starting substring, right? So it's a prefix, not a suffix. So prefix would tend to follow exact contiguous words, right? Whatever that occurred in word, a subset or a substring of a word which occurred exactly in a contiguous manner, that would be the prefix, right, as the name says, and false otherwise, right? So if the prefix exists in the given store, then return true, otherwise it's false, right? So they have given one example that they will go ahead and then instantiate like this, and then they will call the insert word and then the search like this, and then that's pretty much basic, right? So let's clearly what they will do as to build the intuition for this, right? Let's start with this. So they are saying try insert apple. So apple would then be inserted, right? So apple will, let's say in my store, let's say I'll call it as a store, I don't know, like let's say that it is a store. In this store there will be an apple, and then search for apple. Yes, the apple exists, and then I would get the output. Search for app, right? Search for app. So search for app is not a complete word. It's kind of a starts with. If they would have given it with a starts with, then I would have written true. But then since it is a word that they are trying to expect, then obviously this will not make sense, right? So search app will always return false, because I do not have the exact occurrence of app. I do not have an entry after apple like this app, right? It's entire word doesn't exist, so this would obviously doesn't make sense. So app, for that it will return false. Then there comes a starts with app, right? So then that is what the case is. So if I just say starts with app, right, so this doesn't exist. So if it starts with app, then app do exist in one of these store. Like let's say this was one entry, application was another entry, apply was another entry. Likewise, how many entries are there? Let's check that quickly as well. There can be around, yeah, I think the total number of calls that are made collectively of insert, search and starts with is of this 3 into 10 raised to the power of 4. So let's say there are around, let's say there are, assume like there are 1000 words like this, right? And any other like example XYZ, right? The simple explanation, I mean most of you would already figured out, right? So this is the exact occurrence of this, right? Exact store that I would tend to insert into this particular store, right? And then the word prefix consists of only lower English letters, so that is what we have used. It doesn't use the white space character, neither it has uppercase letters, neither any special symbols or as such. The only constraint that they are trying to give is word length, and prefix length is of about 2000 long. Oh, okay, so 2000 long, as in even this entire stuff would be what, around if I just use a word calculator, word counter, if I just put it over here, it says around 626, right, with characters including spaces. So we can imagine it might be a bigger word than this, right? So imagine this entire as a, not as a sentence but as a collectively a big word. So whatever the algorithm that we're gonna come up with need to be optimally it need to be optimal enough so that it fits in this all this kinds of a scenario, right? Right, where were we? So we were in the search of app, right? So we wanted to search start with app. So does app exist as a prefix? Does a app exist? Yes, it exists at multiple location. So yeah, then the obvious answer would be true. Insert app, particularly go ahead and then insert app as well, like this, and then say search for the complete word app. Do that exist? Yes, now it exists, right? So that's pretty much the problem statement is, right? So the overall idea here is I could directly try jumping into the try data structure over here, but before to that, why don't we, I mean, imagine that we are not given this clue that it need to be a try data structure. What is a minimum intuition that we can come up with, right? So for anything that need to be searched, why don't we use a simple hash set, right, for this, right? A two hash set principle here. So where one we would take a simple hash set for words, right? Let's call it as words, as it's an internal data source. So let's say words store, and then where would we within which we would try to add up all these words, entire these words. What would happen is that we will go ahead and implement it, but then the insert would take O of one time, and the search will also take O of one time because it is a direct hashing, right? But then starts with wouldn't work, right? Start with will not work for a single hash set. We have to, for that, what we have to do, we have to use another thing called as word prefix store, which will again be a an hash set again, where we have to preemptively, as in we have to ahead of time, we need to calculate the prefixes of individual values, example individual entries, while we are trying to insert, right? So if I just take apple to be inserted, so the word store would end up having this apple, whereas word prefix would have all the permutations of this valid permutations, as in for the prefix whatever the valid permutations are, right? That is a, and then ap, and then appl, and then apple will, as a whole, apple doesn't exist because it exists in word store, and then it is a complete word, right? So this is not a valid prefix, right? So even if you say starts with apple, I would say that it would end up giving you a correct answer. It has to return true, whether you will give the entire word with for the search or with a starts with. I think it has to return true. So in that case, I don't know whether let me know, but then this is also a valid entry in word prefix store is what I assume, but in any case, store, store, right. So ahead of time we are trying to calculate all the prefixes, all the permitted prefixes ahead of time into this hash set, right. So yeah, this would serve the need as of now. I think the given test cases are sufficiently liberal enough that this solution which contains two hash set as of now would be accepted. But is that the scope of this entire implementation? It may explicitly call out and say that to implement a trie data structure, but is this optimal enough if we need to use a two hash set? For that, right, we need to understand what's the difference between. So here the main reason of not going with a two hash set is that we would end up pre-computing all this ahead of time, right. At any point in time, starts with may not be interested in APPL, or it may not be interested in app, or it may not be interested in AP, but then as a whole we need to pre-compute it and then make it sit in a particular hash set. We need to hash them up. So there is a larger complexity in terms of wastage of computational power for this. First is that, right. And let's quickly go into the diagram where I have given where I have tried to make a difference between what an hash set two hash set implementation versus a trie implementation would help, right. Try understanding the differences in between these two, right. So yeah, this is one such so two hash set approach. So what we are trying to do, we are hashing the entire word and also the possible permutations of all the valid prefixes. What will happen, as we all know, that the high space overhead hash set stores full substrings redundantly, right, as we discussed it before. So whereas trie, what does it do? Since we all know what's a trie data structure is, so trie as a whole, what it does is, if we quickly you don't know this, so what does a trie structure look like? It looks like a typical tree. It's a tree data structure where it is hierarchical in nature and the flow grows from top to bottom. And then what we do is, at the end of each word formation, we do maintain an indication that this is an entire word, right. So to quickly give you the introduction to trie, right, visually, so there is one such app over here, right. I will link this particular person's this URL in my description as well. This I found it to be very handy while I was trying to see the visualization for this. But in any case, kudos to this guy. Go ahead and then star him as well. It would help such open source contributors, right. In any case, quickly coming back, so in order to understand how does a trie look, right, so this is one such indication. So this is a little bit of a very big picture. So for this may look fuzzy to you, but bear with me, right. So try visualization with a simple, let's say an apple. How does that look? So let's try inserting it, right. See how does it gets, yeah. So this is how exactly that it gets created, and you see that there is a word in the trie as of now, that whatever that is there is apple. And if I do this app as well, it just makes a pointer over here, that it means that it is an indication of the entire word that stops over here, right. So that is what it says. So app is an entire word, apple is an entire word. If I just say application, let's process that as well. So it's kind of a yep, yeah. So let it fully render. So yeah, this is the entire how does a trie look like, right. So what does trie do is that it goes ahead and then creates a node, and it keeps on creating the further nodes until and unless it reaches the end of a given word. And for that end of the word, it maintains a kind of a boolean or value where it says that this is the end of the entire word, that this path that it takes, that it would be a word, entire word, right. So that is what it does. So this trie is as similar to that of a tree, where it maintains a hierarchical form starting from start to end, right, simply. And each of this node contains a multiple neighbors. For an example, look at this. So look at either the root, or even root itself is also an a node to start off with. So entire data structure can be traversed, the Trie data structure can be traversed through using this root, right? Look at I. So each I, whatever the node it has, so individual node would have n number of children, right? Not neighbors, because those are literally, because since it is hierarchical in nature, so they will be children, right? So there may be multiple children to it. So each children could be persisted based on either in a form of a dictionary, or at a primitive level it can be an array of a lowercase letter. In our particular implementation, it can be an array of lowercase letters like this, right? So imagine I would then have a baby, right? A baby is inserted, so it starts with B. So each individual root or any node individually would have, see, I can go up till zebra to be implemented. So what I'm trying to say, between AB and not between AB to Z, there can be multiple other words as well that may come up as a complete word or a prefix. So it keeps on persisting in this way, right? So let's do a random initialization and see the landscape of this particular tree. See, this is the Trie data structure. So where the root would have a memory pointers to all these starters, right? And then each individual word would then also lead up to kind of a linked list. Linked list would then be a very vague word to use. It's kind of a tree data structure, right? So each individual node would have multiple children underneath it. So yeah, so that is what a Trie data structure looks like. Now, since we have introduced what is Trie, now we are in a good position to understand how a two has set approach will sound to be a redundant and kind of a time consuming approach as compared to that of a Trie data structure. Let's now quickly go through the difference. Why shouldn't we go for a two hash set approach in this case? A hash set stores a full substrings redundantly. As you have seen, a given app will be split into AP and APP as well. But as in case of a Trie data structure, you see this APP, only individual nodes are getting stored here, no redundancies. Each individual node would only encapsulate that particular letter or a memory address or a pointer to that particular location, only that much, right? So there is no redundant prefix calculations. That is one, that it saves space. Then the insertion overhead. The hash set requires O of L squared to generate all the prefixes at the insertion value itself. At the time of insertion itself, you have to pre-compute all the prefixes, or probable prefixes which would be hit as well, which would not be hit as well. As in, I may not search for a possible prefix. So even then I have to go ahead, but because it is a possible prefix that at some point in time that may be hit as well. There might be some optimizations that we can do, but then the overall complexity is that it is O of L square, that it need to generate all the possible prefixes beforehand. That's the insertion overhead. But whereas in case of a Trie, all that I have to do is maintain an hierarchical relation. Even though whether the particular prefix would be asked for or it will not be asked for, it doesn't matter, right? Whether I gonna ask the Trie data structure to give me a starts with AP, then it will give out, because all that it has to do is that it has to need to traverse that particular Trie data structure. That's all. So there is no overhead computation. The structure itself is self-sufficient, that it can suggest what? It can suggest the start with operation, right? Any type of head feature. So that is what major distinction between the storage overhead and the insertion prefixes calculation overhead, computational overhead, are the two major things. And one more thing is no structural insight. This is yet another bigger of a feature, not for this particular problem, right? So for a feature of, let's say you want to implement the suggestion part. Example, if I have to, like a typo head feature, right? If I am trying to type up Apple, when I am at APP, LE need to be auto completed. So for that, the hash set doesn't work at all, because hash are randomly calculated and they are placed in a jumbled order or in an hashed order. Whereas in a trie data structure, all that I have to do is that I have to see all the children of P, right? So at P, if somebody types AP, what are the possible paths that it can have? It can complete to PLE, which is an apple, or it can complete to T, which is an apt, which is a complete word. It makes total rational sense, right? So such is what the power that comes from structural insight. So with this, I think the given problem, we can do it with using 2 hash set, but then this doesn't serve as a entire insight, so we would end up using trie in at any point in time. So let's quickly try implementing the trie data structure, right? So for that, what we have to do, the intuition is very simple, right? So each individual node, as we seen here, let's go with this visualization which we did here quickly. So let's refresh this. What is that? So let's go with apple. So every single node contains what? Contains a pointer location to a next immediate node, right? And it do contain something of a root. If given a root, then we need to be able to traverse the entire stuff. So how do we do that quickly? So we need to come up with a simple node, right? So we will say public, right, or let's say wait, private what, let it be a sealed class, right, sealed, what is this class, and trie node. Let's go with this, right? Let's create a trie node where it contains what? It contains, as of now, we can just go with lowercase English letters, right? It just says simple lowercase English letters. I can make it 127 character, but then it is not required. So let's start with a simple a kind of an array, right? We need pointer locations, very simple. That is what it shows, right? A simple pointer which particularly points down to n number of around 26 characters of neighbors that it most probably will have. So for that, I have to just say an array of what we would say, not neighbors, particularly children, right? Children, right? And then, so yeah, simply this. And then we need some sort of an indication that this is a complete word. That particular node, this particular node is an int. Otherwise, this is not it's not a complete word. For that, it would stay false. For the one which has a complete word, then it will state as true. So for that to happen, what we can do? So we can maintain a bool value and say is word, right? Simply is word implementation. Sorry, yeah. Then that's all. So what I can try doing is public, and let's pull up a constructor to make it quickly to initialize. So what we can do, so these visibility levels should be public for both of this, right? So here in this particular one, so let's say trie node for this. So let's quickly copy this trie node, and then we will initialize this value. So children will be what? Children equals to new. So can we do this? No, we can't do that because it is an array, right? So we can just say 26 long, right? And then is word would be equal to false. Done. Right. So quickly, what else is needed? So we need to go to root, right? We need to implement this root quickly. So let's start up with this root, right? So this again will be a private one, right? Private, and it need to be read only as well, because accidentally you don't end up corrupting this value, so that it has only the initialization in the public CTOR that we have, right? So private read only, what we have is a root, right? So root is of the type trie node again, right? Trie node, and let's say root. Okay, so all that we have to do in this public constructor is that we need to initialize this with, we need to new it up, That's all. Now let's quickly see how can we insert into this particular data structure, right? All that we have to do is that we need to go ahead and then iterate, right, till the word ends. So for that to happen, all that we have to do is we have to write a for each, right? For each individual character by character. Let's say in word, what is that we need to do? We need to start up with, right, character by character. We need to start with that, and we need to build the relation, right? For that, let's do the typical linked list kind of navigation over here. So for that, which we will do is current, right? Because it's kind of a linked list, right? So it's kind of a which is pointing to another location, and then it has a pointer to another location. Only thing, the difference between the linked list kind of a traversal versus a traversal is that it may end up having not one forwarded node or a next node. It might have a n or 26 in this case, a forward or a next nodes, right? So we need to be little little cautious while we instantiate what the next node would be, right? For that to happen, all that we need to do is that current will be present root, as we would do in kind of a linked list traversal, right? So then we have to check if this current node, whatever the current node that we have, right, and its children, one of its children, right, does this have this implementation, and then that is what we need to see. So this is how we will go ahead and access a particular neighbor, particular children for this case. So, and if it is not equal to, if it is equal to null, go ahead and then create it, right? So current.ch would end up having a newer version, right? Otherwise, if it is already present, what is that we need to do? We have to navigate so that we further down wherever the initialization has not happened. Example, in this case, let's say application or apply, right? So what will happen is A would have been already existent, L would have been existent. Only at L we would try to find out whether Y exists or not. In order to find out Y exists or not, what is that we need to do? We have to just get to the place where L is there, right? To this place, there is no new up required up till this point. And then at Y is something where you would go ahead and then create up a new node with Y. I mean, that's for that particular location, right? So in order to traverse further, what is that we need to do? We need to say current is equal to current children, right? That's all. So this, I think so, should be sufficient enough to insert, right? Yeah. That's all, I think so, for the insert part. So how do we go ahead and then search? Search would be typical again. So for the searching part, right, it's as typical as that of insert, but only one catch is that we are trying to search. So in this case, so search is there, right? So we are trying to search this. So see this visualization, right? And it says the apply is not there, as you see in the word that is just apple, and then in visualization as well. So what it did, let's do it once more. So it went node by node, right, like we did it in insert, and only at the very end that it tried to find out whether a particular Y exists or not. If it didn't, then just return back false. So instead of not returning anything, we have to return false. So we have to typically copy this entire stuff, right? So we will start up with current, go word by word traversal, right? If this particular thing is null, that would happen where in case of Y. So all we have to do at that time is that we have to return false. That's all. And if it is there, if it is present, then keep on going to the very next one. So at the end of it, let's say we have traversed the entire stuff. For an example, if I just go here and if I, let's say, apply apple, in this case, what would happen is that it has to come till here and say it should detect a word ending. It final check will resolve around whether the last node that I am on, that is the current node that I am on, that's the very last of the iteration, right? Current node, does it contains is word? If it is there, right? If it is totally dependent upon this word, so I can just simply written this guy, right? You are right, that's all. And what will you do? That's all about, I think, about search. This will go about a typical word length and then try to find out whether this particular word exists or not. So how would you do a starts with? All that you have to do is that you are not worried about whether it is a complete word or not. In case of an app, there is no search what do you say, starts with implementation over here. So simply said, all that it has to do everything that it did here, basically, right? There is a kind of, you would see that there is a repetition, right? You are repeating yourself. So we will get to that part of optimizing involving some clean code principles. We will get to it in a minute, but before to that, let's complete this implementation. So all that it has to do is that it need to traverse like we did it in like previous two conditions in insert and search, but the only difference is that it need to return true at the end of it, because it doesn't matter if it has come till here. It doesn't matter whether it is a complete word or not. It is present in the entire in the tree that we have, right? Let's quickly see any syntax error that we have, right? There are many. Public, what's the point here? It's a private. It is saying yeah, we missed this part. Okay, so try node, let's see whether it works. Okay, what's the issue here? So we do have this children node. What's wrong? Public tree node, what does it say? Namespace tree node, right? Okay, tree node could not be. Are you missing a directive assembly in the solution? The name word does not exist in this current context. So yeah, this okay, so tree node, right? Tree node is this tree node, right? Did I spell it wrong? Let's do one more. I think, yeah, I think I did I spelled it wrong is what I feel. But in any case, let's go to the next one. That, okay, word doesn't exist, it's prefix. Yeah. Okay, let's see. Are there any logical or syntax errors such, or it would pass? Okay, there are two test cases. This passed and then this one failed. Why did it fail? For which condition did it fail? Should have written. Okay, so we haven't set the current is word while we did the entire insertion, right? We haven't set it. We haven't logically formed that it is a complete word. So for that to happen, so current is word, right? The final word should be set to true. With that, I think it should resolve. It's basically, we are trying to say that this is the complete word, right? At the end of our insertion that we have hit the, okay, at 0 milliseconds. So it did compile at a good amount, not a bad time to start with. Let's do one more. Okay, I think I hit it. Let's see. Yep, we are at a very pretty good range over here, which is 15 milliseconds, right? So it's a good range. So you can look at the other implementations as well, so that you get an inspirations of how they have tackled the given problem, right? So now looking at this implementation, right, this is not a bad implementation as part of algorithm and LeetCode computation is concerned. This is not at all a bad code. It do compiles within what, around 15 milliseconds, even lesser to that. It's not a bad time to have as well, right? But then would it be acceptable as a library? I don't think so because we haven't followed certain concepts. Like let's let's try doing that clean code implementation upon this, and try making it as a good library that other fellow developers could utilize, right? So we are ultimately doing what we are trying to bring up. We are trying to make it a, a custom data structure, a Trie data structure. So at least it need to stick to some good coding practices. So it starts with applying some of the oops concept, some of the clean code practices, where we are, see, look at this, we are repeating ourselves for here by using this kind of this, at least this logic is redundantly used, so we can try optimizing it. However, see, we have two test cases at least to play around with, right? So if at all, if we end up making this any kind of a wrong implementation, logical or otherwise syntax as well, so our test cases are there to figure out and give us kind of a, it's kind of a built-in TDD nature, right? So it's a kind of a test driven development as well, because so we already have a fully working code which compiles at around what which compiles at around 15 milliseconds as we checked. And now whatever the changes that we have to make over here will be caught by such test cases upfront and need not worry, right? So that's the whole idea of test driven development would be, right? So let's try implementing kind of a clean code principles. So already a proper encapsulated one, you see this is already a private sealed, it has a scope until and unless we know that there is a implementation that need to sit outside, we would try to keep everything encapsulated and sealed within our assembly or within our application itself, right? At some point in time, let's say we figured out that there need to be an inheritance associated with this particular tree, then we can come ahead and then qualify it to be inherited, right? Till then, let's make it sealed class. That's second. Let's improvise on the kind of the access modifiers, right? So it is private, properly kept, public, properly kept again. So we could try having some getters and setters, so that we can see that tomorrow, if at all, if we need to have a private setter or a getter, there is a way to do those as well. So that's one thing that we can try doing. And moreover, look at this implementation. So yeah, we will get to this converting this into a dictionary maybe at later point in time, but as of now, let's optimize the other stuff. Okay, so yeah, this looks to be good enough. We have already used read only, right? And then we have started with insertion. So insertion looks pretty straightforward, right? So these are the two ones that need to be groomed a bit. So what we can do is we can try using do not repeat yourself kind of approach here, right? And make a private class, sorry, no, a private method which returns a kind of a node to us, right? A tree node to us. Let's copy paste the try node, so that, right? And we'll also make it a nullable one. I'll just explain in a bit why we are making it a nullable one, right? Private try node, all it will do is it will implement a get node, right? What this guy will do, given any query or any path that I need to query upon, the query would be the appropriate word to use, it need to return that node, and it is up to the implementer whether if it is a search, what it has to do, it has to further go ahead and then probe that particular node. So what it will do is whatever the word or a query that you have given, it will traverse till up until that point. Let's say example, I have given search for apple, so what it will do is it will go up till the very end of that apple and return that node. If there is no node, let's say I have given apply, so that there is no node to that, then it will return off null. That's where the try node is made nullable, right? So what will happen is the implementer would then check, if it is a search, then it will check whether that particular node has is word in it. I mean, try doing is quickly, we can take this implementation, paste it over here, right? Current is root, and then whatever the query we have is this query. And what is that we need to do? If the current children, right, is equal to null, this means that if it is null, then you need to return off null, right? If not, go ahead and then go to the next immediate child, and here I have to return the current node. That's all. And here in this implementation, this entire implementation now can be substituted with a single line. Where in this single line, just a second, okay, yeah. Where in this single line, what I will do is I'll just go ahead and call this get node, right? Get node would then have word, and then what I will try doing is, if this particular stuff is word, right? If it is word, if it has a word, then if it has a word, if it returns off null, what do I have to do? If it is a word, then go ahead and then return it. If it is not a word, then return false. That's all. So all that it is doing, I mean, you can just try, if this is a complex of a logic to you, what you have to do is, this is using null coalescing operator as well, and it has a null checker as well, right? So basically all it will do is that whatever the node that you got, check whether it is a complete word or not, right? The word ends there or not. If not, then you return off false. If it is so, then return true, whatever the implementation that was there. Let's quickly check. That's the beauty of having a test cases written up front, right? So I'm missing a semicolon somewhere. Oh, okay, so this doesn't require semicolon, right? And then we will refactor this method. Okay, it works. So now our test cases are happy. Let's refactor one more stuff now. So that's how typically a TDD is done in any production environment, right? Whenever you are doing an active development, this is how you have to do. So now we are trying to make up another refactor for this. So for this, what I will do is I'll just entirely kill off this. So what was around around a 60 line of code now is reduced to a consigns bit, correct? Okay, so here again it has to call upon this get node with this given prefix, and then literally I have to just check whether it is null or not. If it is not equal to null, then that means that that particular prefix exists, and let's check that. If it is null, then that means, yeah, that it works. Yeah, if it is not equal to null, then that means that the entire prefix exists. If it is equal to null, then that probably, in this case, right, when we go to this visualization, let's say the check is for apply. So for y, what it will do is that it will try to traverse till up until L, and then try to figure out why doesn't exist, then it will return off null. So if it is null, then that means that that particular prefix doesn't exist. Okay, this seems to be good enough, right? And we have passed these two test cases. Okay, let's do a submission. And I think so what will happen is, in our millisecond scale, right, we will try to shift, we will do a right shift, right? Obviously, because all these computations, extra computations would take some overhead. We are at 18 milliseconds. So let's further optimize this. What are the other optimizations that you can bring in? So this is at least it has a complete sealed class with private access modifiers and all that. What else that we can try doing with this? So we can try making it more generic. So see, look at this. We are since we are trying to offer this as a library for other fellow developers, right? So what we can try doing is we can flip this to be a dictionary, right? So what if going forward we have an uppercase support, we need to extend to an uppercase support as well, right? For that to happen, so it need to be more generic one. So let's flip this to dictionary. Particularly, let's make use of something of a concurrent dictionary, right? Why concurrent dictionary? Concurrent. Let's make use of concurrent dictionary. Why particularly concurrent dictionaries? Concurrent dictionaries are thread safe, right? Whether we are doing a search or an insert, we would end up doing it in a thread safe manner. So this exactly why the use of a concurrent dictionary would come up, right? So let's flip it to a concurrent dictionary. Not only that it will be versatile to all, supporting all the letters, but also it would then be thread safe as well. So let's import this. I don't think so it will be defaultly imported. So let's use using statement and see it. I think it sits in the system concurrent space collections, right? Collections and concurrent. I think if I'm not wrong, then it should exist within this, right? So concurrent. So let's check with whether the compiler is happy or is it complaining about this statement itself. Okay, it is happy, and it's obviously we need to give the generic type. What would be the key for this? Will be the character key, right? And what would it end up storing? It would end up storing the trie node, right? The reference to that particular trie node, right? Is it happy now? See, the having test cases up front, we can play around it any number of times and then go on confidently refactor our code, which also gives us confidence while we do this sort of development. Points down to the next refactor that we need to end up doing as well. So it is complaining you are instantiating in this way, so that is not at all the way to do it. Okay, I think that's, yeah, we can do like this. Okay, yeah, it is happy now. Yeah, so this entire chunk boils down to a one single chop. Look at this. The optimizations that I can end up doing is very simple. All that I have to do is current. What is that we were trying to do? We were trying to get the existing node or trying to create up a new one. That's all we will do, right? So it offers one good implementation where, so current, whatever the current that we have, right, the children particularly, all that we need to do is that we can have get or I think so it is get or add, right? Get or add for what? For this particular ch. Hopefully that should work. Let's see. Get or add. Okay, get or add doesn't exist. Nullable references, nullable context, no overload method, get or add. Okay, get or add what? You have to specify that. You have to make it a function, kind of add new tree node, right? And it is implicitly understood that I am trying to new up a trie node. Yep, it is happy, it went into the next place. So yeah, here all that we need to do is that we need to check, right? This particular implementation is null or what, right? So for that to happen, all that we can do is we can use yet another function, current children. For this is what? Current children get, I can use try get value, right? Yeah, I think I can use get value here and say out with, not out, particularly what is that we are trying to query is for ch, right? And then there is already a current declaration, so all that we have to do is out with this current, right? If current is null, right? If current is null, if current, return current. That's all I think so we need to do here. What if it is null? It will return that, just simply return cu, right? Current, and current will be already be pointing out to the next immediate one, so no need of this, right? If it is true, then do this. If it is not, return null, right? That's all we need to do. Let's check. I think there is too many returns over here. What is that we need to do? Yeah, I think we need to say if we are unable to discover, so there is a one test case failure, right? I think I made this logic wrong. So if there is no present, if there is no particular child exist, for that what we have to return? We have to return null, right? If we have one, then proceed further. That's all. Proceed further, right? Proceed to the next current node, which is proceed to the next node, right? And then finally, let's say we are at the very end. What is that we need to do? We need to return off current. I think they should work. Let's check. Yeah, it worked. And then you see that it was 0 millisecond and then we shifted towards the right. So that would what happened, right? As soon as you implement these concurrent dictionaries and all that, there will be a overhead, but then that would end up being a thread safe dictionary. That's the hit that we're gonna take. Thread safe, that's a valid hit that anybody should take, right? It is thread safe now, number one. And here we have a proper inheritance, right? Inheritance, at least a control over an inheritance on our library. And on top of it, you see that it is properly encapsulated as well, right? Encapsulated, right? It's properly encapsulated, right? And this is again following that principle. And then you see that instead of eagerly loading and newing up over here, we are doing a deferred initialization, right? This is also one such good practice. We have deferred initialization. I think we can also lazy load. In this case, there is nothing heavy to be lazy loaded, but then this is a deferred initialization, which is good practice to do, right? And again, here we have used a read only so that we don't accidentally corrupt this value, right? Accidentally manipulate the value, right? That's how any library implementation should look like, right? And what else we have used? Not to repeat, we are not repeating ourselves over here, that I think. So this is a pretty good library to start off with, right? And we have thoroughly made use of all our test cases, right, while we confidently refactored our code, doing a bit of TDD, and then we are at the very end. So this is what it proves, right? Around 10 milliseconds to start off with, 15 milliseconds to start off with, and then we are kicked back up until around 100 milliseconds, in the range of 100. This happened because this particular 16 test cases which they have written, I think so they have written only to be optimized for a 26-bit long array, right? If we start using dictionary and then we try making it concurrent dictionary, the hashing and the hash computation would intrinsically have some impact on the computation wise. But then this will be a good a good library to have. Look at this, where we were at around 15 milliseconds. You see this code which has like 50 lines of code, whereas we have just reduced only 5 lines of code. That's okay, but then we have used comments and all that, so around 10 lines of code we have reduced. It's not about reducing the lines of code. We have made use of inheritance, a proper control over inheritance. We have made encapsulation, we have used thread safety, we have deferred the initializations, right? We have used read-only modifiers, we have not repeated ourselves. These are the kind of clean code initiatives that we have tried making use. Hopefully this was interesting to you, right? This is what the bigger picture of implementing Trie looks like. We started off with why not use an hash set, to going into why using a Trie, what is Trie, quickly understanding that and making a good implementation, and then trying to refactor our ways by using TDD principles, and then trying to make it work. A good amount of clean code is what we have written, right? Hopefully you enjoyed this doing. I did enjoy thoroughly while I did this work along with you guys. Let's see with another implementation in another video. Meet you guys over there then. I'll take a bit. Thank you.